Hi, and welcome to this talk. I'm Armaël Guéneau, and I'm excited to be presenting the work done with my co-authors on obtaining theorems for free from separation logic specifications. You might have already heard about this idea of theorems for free from the work of Reynolds, Plotkin, and Wadler in the context of polymorphic types. There, the idea is that if you know that some program has a given type, for example, for alpha, alpha, arrow, alpha in system F, then whatever this program might be, you can get a free theorem about the behavior of the program. For example, here, that it is actually contextually equivalent to the identity function. And this kind of equational property is a free theorem in the sense that it holds of any program of the type, just by looking at the type. In this work, we applied this idea of theorems for free in the context of separation logic specifications. Intuitively, for a library that satisfies a given separation logic specification, this specification restricts the way the library functions can be called. And thus, it can be understood as defining a set of legal traces of interaction between the library and a client. We show that this intuition can be made actually precise, and that we can thus obtain theorems about the interactions between a client and a library, depending on their specification. Let us consider a concrete example. So here we have a separation logic specification for a minimal file library giving access to a single file. Initially, the specification gives us the closed separation logic resource, which specifies that the file is initially closed, and we also get the specification for three operations. The open function opens the file, consuming the closed resource and producing the open resource. Read leaves the file open, and finally close consumes the open resource and gives back the closed resource. These open and closed predicates are abstract, so a client of the specification can use them as abstract token but cannot unfold their definition. Then it seems quite clear that a verified client will not be able to call the functions in any order. In fact, any client will call the functions in an order that corresponds to the automaton shown here on the right. And this is a property that I will show how to prove formally later. It might seem fairly obvious at that point, but it's important to note that it does not follow from any standard model of separation logic, so we'll have to do something more. Then we can consider more expressive separation logic specifications, which enforce even more interesting interaction traces. So consider the specification for a library of mutable collections. We have operations add and remove, which modify the collection in place, an operation iterator, which produces an iterator on the collection, and a function next, which can be used to get a new element from the iterator. Now, this specification is quite expressive. And indeed, a maybe seasoned practitioner of separation logic can look at it and say, yes, I can see that this specification prevents iterator invalidation. And, well, indeed, add and remove generate fresh collection identifiers, while next requires an iterator and collection with matching collection identifiers. So it does follow that for any client of the library, an iterator is only used with next as long as the underlying collection has not been modified with add and remove. What we provide is a formal framework for establishing this kind of results. That is, deriving free theorems as trace properties of client library interactions from separation logic specifications. And we apply this approach not only to reason about challenging sequential specifications involving iterators, higher order functions, specifications relying on well-bracketing protocols and full functional correctness, but we also show that it scales up to allow reasoning about concurrent library specifications, for which we prove the general result that logical atomicity entails linearizability, and so more on that later. And finally, the whole work has been fully mechanized using Coq and the Iris framework. So what was the challenge? Well, the main challenge was in fact in finding how to even state formally the free theorems that we want to obtain. In the case of parametricity results for types, free theorems are formulated as equational properties relying on contextual equivalence, which is itself easy to define on top of standard operational semantics. In the case of separation logic specifications, however, we wish to prove a different kind of properties, namely trace properties about calls and callbacks between client and library. And for that, we have a problem, which is that these interactions are not easily observable. Indeed, the distinction between client and library is first really only exists at the logical level. At the level of the operational semantics, after library and client have been linked together, the calls between the two simply become indistinguishable from other reductions of the program. But we can try anyway to write down formally the shape of a free theorem and see what the problem is. So what we would write is that we consider some library lib satisfying a specification phi, a client verified against phi, and then when those are linked together, they should interact as described by phi. The first part sounds okay. Indeed, the theorem should still hold if we swap in a different implementation for the library or the client. But the second part is clearly no good because it's still too informal. So what can we do? Well, the key idea of this work is to add a spy. So instead of directly linking the library with the client, we will implement an additional piece of code W, which acts as a wrapper on top of the library and is going to spy on its interactions with the client. The wrapper assumes a library satisfying specification phi, and itself implements the specification phi. So from the point of view of the client, the wrapped library is indistinguishable from a normal library. But additionally, every time there is a call between the library and the client, the wrapper will record that this call has happened by emitting an event which gets recorded in a global trace. So the recipe is as follows. Given a specification phi, we first implement a wrapper that observes the call between library and client. And then we will prove that the trace of events emitted by the wrapper satisfies some trace property of interest, big L. And L can be, for instance, the language for the automaton we saw earlier. And if we do these two first steps, then we obtain, as a free theorem, that for any library implementing phi, for any client verified against phi, when we link together the client, the wrapper, and the library, then for any number of reduction steps, the trace of events that are emitted satisfies the property L. Now, on a more technical level, we need in the wrapper code to be able to emit these events I just mentioned. So we extend our otherwise standard programming language with a new emit primitive to emit an event. And we also extend the values with labels, which are just strings that can be used to identify different events. Then the semantics of emit v is simply that it reduces to unit while emitting v as an event, and a trace is simply a list of values. As we will use separation logic to reason about the behavior of a given wrapper, we also extend our separation logic with predicates to talk about the trace. There are two of them. The predicate trace t asserts that the current trace is exactly t. And then the predicate trace inf of L asserts that at any step, the trace must satisfy the trace invariant L. And then these predicates allow formulating a rule for emit, which requires proving that the new event which is being emitted preserves the trace invariant. Now, let's make things more concrete. We can come back to the specification for the file library we have seen earlier and see how we can apply our recipe for free theorems. The specification is the same as before. Then we define our wrapper program, where each instrumented function simply calls to the library function and then emits an event with the corresponding label. Then the trace property that we expect of these emitted events is given by the automaton we've already seen. Formally, we write LC for the language corresponding to the state where the file is closed, LO for the language where it's open, and LFile, the trace property, as the union of the two. Then we need to actually verify our wrapper, and we prove that, assuming some library lib satisfying the file specification, and given separation logic resources for the event trace, then the wrapper also implements the file specification. And notice that with this trace inf resource, we specify that our language L file should act as the trace invariant. Then there are two steps to the proof. First, recall that the definition of file starts with there exists abstract predicates open and closed. So we can actually choose what we want to use as predicates open and closed for our wrapper, depending on the close and open predicates for the lib. And we define open as holding the open predicate for the lib, plus the fact that we have access to some trace T in LO, the language for the open state of the automaton. And similarly for closed, we have a trace in LC. Once those are defined, we can complete the proof by verifying the specification for each instrumented function. For example, for open, we need to show the following triple. And then the first step of the proof is simply unfolding the definitions. Then we apply the specification for the underlying open, which turns close to open. And finally, we have to justify the emit with the open label by showing that the trace invariant is preserved and that the trace indeed goes from belonging to language LC to language LO. And this holds because we have a corresponding transition in the automaton. Finally, as per the recipe, we get, as promised, the same free theorem as was written before, instantiated with our specification, trace language, and wrapper code. While the file example is sequential in nature, interestingly, we can apply the same approach for reasoning about much trickier properties that arise in a concurrent setting. A library which exposes a concurrent operation up has to handle the fact that this operation may be called at the same time in different threads. So to specify what it means for such a library to behave well in that scenario, the notion of linearizability has been widely used, where a library is said to be linearizable if one can reason about it as if the operation were called in a sequential fashion. In other words, one should be able to shrink conceptually the time span of each execution around a single so-called linearization point, while still observing the same results. And because linearizability is a very explicit property about the execution trace of the program, a different concept called logical atomicity has been used in some advanced separation logics to express linearizability, but in more logical terms. And the idea then is to use a different kind of special triple to specify concurrent operations, which guarantee that the operation will update in one step the resources in the precondition into the one in the postcondition. And it was understood informally that logical atomicity was indeed expressing the same thing as linearizability. Well, in this work, using the approach I just presented, combined with some more advanced separation logic proof techniques, we can actually prove formally, as a theorem, that logical atomicity indeed entails linearizability. And there are more details about the proof in the paper. To wrap up, I showed in this presentation how we can formally obtain free theorems about the calls between a library and a client, given a separation logic specification describing the interface between the two. We can even draw a comparison with how free theorems are obtained from polymorphic types. Where types give us equational properties, we get trace properties. For types, the theorem is free in the sense that it holds of any expression of the type. For us, it holds of any library satisfying the specification. And finally, in the case of types, the key insight one needs to come up with is in typically choosing the right relation to instantiate the relational model. In our case, it's in picking the instrumentation and the wrapping abstract predicates. If you want to know more, the code formalization and the paper are available online, and I'll be happy to answer questions as well. Thank you for listening.